Hello Chem 212 students, and welcome back for the third lecture video and the final one this week. This is about the last few sections in chapter 2 of your textbook regarding the stability of various resonance structures. So in the previous lecture, we talked about how to use double-headed arrows to represent the movement of electrons in resonance structures. We also talked about what a resonance structure is. It's two drawn structures, that two or more, could be many, that represent the various electron configurations in a molecule. But the actual molecule is the hybrid of all of these. It's the nectarine analogy your textbook uses. A nectarine, is it more like a peach or a plum? Well, it's something in between, but it may not be exactly halfway between each structure. Some structures are more stable than others, and so the electrons will spend more time in a particular arrangement that we drew rather than another. And the electrons are constantly moving, but we can kind of weight the structure towards what it would be mostly like. So molecules often have many resonance contributors, but not all of these resonance structures contribute equally. And so the actual resonance hybrid will resemble the actual stable contributors. And the way we know this is we can take a look by various spectroscopic measurements. By shooting light at the molecules, we can know what their bond lengths are like, and we can figure out how much energy it takes to break a bond. And when we do that, we find that, you know, a bond that looks like a halfway between a single bond and a double bond in a resonance structure actually has the properties that would exhibit a 1.5 bond in terms of the strength of the bond and the length of the bond. And so so what the molecule will look like, the length between the bond length between atoms and the bond strength will depend on the nature of the exact resonance hybrid that's being discussed. So how are we going to assess which of the resonance structures that we write is most realistic and representing of the actual molecule, and which ones are less realistic and less representing of the electron configurations in the molecule? Generally, if there's formal charge on a structure, that indicates lower stability. So the most stable structures are generally those with the lowest amount of overall formal charge, particularly if there's a positive formal charge on an electronegative atom, or a negative formal charge on an atom with low electronegativity. For example, we would not write resonance structures generally, or they're less stable. We would write them sometimes, but resonance structures with a positive formal charge on oxygen are definitely not very stable. Or resonance structures with a negative formal charge on carbon are very unstable. And then in terms of stability, having complete octets, of course, for our second row elements, you can't exceed an octet. But for carbon, for example, you could have 6 electrons. That would give it a positive formal charge. You could have 3 bonds, no lone pairs. That would give it a positive formal charge. But that's a low stability situation. And so let's take a look here for potential resonance contributors for acetic acid. So here's another example of that, and we can decide which ones we think are going to be the most stable. First of all, this oxygen, it's got no formal charge right now, so it's making 2 bonds with 2 lone pairs. So there's the lone pairs. This oxygen, also no formal charge, so it's making 2 bonds with 2 lone pairs. And so we've got a few possibilities here. The one we could go for first is that we have a pi bond between 2 atoms of differing electronegativity. Oxygen is far more electronegative than carbon, and so we could have electrons moving up this way. And so now we can draw that structure. So that structure would now involve a single bond to the oxygen, and the oxygen would have 3 lone pairs, so that would give it a -1 formal charge. Now this carbon is now making 3 bonds with 0 lone pairs, It was making 4 bonds with no lone pairs, but now it's making 3 bonds with no lone pairs. So it has a positive 1 formal charge. And then this oxygen here is still just the same. So there's one contributor. And then we've got one more, because at this point we've got a lone pair that is adjacent to a positive formal charge. So we can make that movement right there with one arrow again, and we can get another resonance structure. And so we'll draw that now. We've got now a double bond to this oxygen, and we've still got this hydrogen here. We've got this oxygen, and it has 3 lone pairs. So now this carbon in the middle is making 4 bonds with no lone pairs, so it is got no formal charge, and the oxygen here has a -1 formal charge due to having 3 lone pairs and 1 bond. This oxygen has 3 bonds and 1 lone pair, so it has a +1 formal charge. Okay, and so which of these would be most stable? Well, clearly the one with no formal charges. That's the most stable. Then this one, it has a formal charge, so it's less stable. However, the negative formal charge is on an electronegative atom, so it's not that bad. It's less stable than the first one, but it's significantly less stable, but it's not terrible. This last one is very unstable, so the electrons are very unlikely to be in this arrangement, because not only is there more formal charge as a negative and a positive, well, there was here too, but the positive charge is on an electronegative atom, so this would be the least stable one. So in terms of stability, it goes from left to right, most stable down to least stable. Here. Now here's an acetate ion, so a very similar structure. However, this time this oxygen has a negative formal charge, and so what that means, it has 3 lone pairs and 1 bond. And so like last time, we can, and there's often more than one way to do this, but we can pick out the fact that we have a pi bond next to an electronegative atom, and so that's similar to last time. That gives us this situation where we have the oxygen with a negative formal charge, and the carbon now making 3 bonds with no lone pairs has a positive formal charge, and this oxygen continues to have a negative formal charge. And now we have a lone pair next to a carbon that has a positive formal charge. So we can do that right there, move that electron with 1 arrow, and we get, now a double bond to this oxygen. So now it has 2 bonds and no lone pairs, so it has no formal charge. And the carbon now has 4 bonds, so it has no formal charge. And the oxygen here still has this -1 formal charge. And so these structures on the far end are equally stable. And so you get basically a mixture between these two. This one in between is highly unstable. And so what we could have done is we could have gone instantly from the first one to the last one if we would have just used our first rule, and that is an allylic lone pair. That would have required a double arrow, but that would have gotten us straight from the first structure all the way to the last one. And these two structures are much, much more stable than the middle one. And they're about 50-50 because they're essentially equal. We can see each one is an oxygen with a -1 formal charge. So another thing too is always keep in mind, as I said in the last lecture, your formal charges are always going to add up to the same thing if you did it right. So if you started with a -1 formal charge like we did here, the sum of all the formal charges must continue to be -1 because you're not taking away electrons, you're not adding electrons. So here if we add -1 + 1 - 1, that's -1, or here we have -1. So if you end up with a different number, different total amount of formal charge than you started with, you know you made a mistake somewhere, and you should go back and check that. Draw the resonance contributors for the following. So we have a number of possibilities here. There's quite a few. So one is that we could start by saying, okay, we have a double bond allylic, like that, right? Or allylic positive formal charge. The positive formal charge is on the nitrogen, which is attached to the carbon on the double bond. And so we could get this structure, single bond. Now note that this carbon down here was making 4 bonds. It had 2 hydrogens here. So now it's only making 3 with no lone pairs. So it has a positive 1 formal charge. And then we have the nitrogen, which is now, oh, I can't do that. Oh, why can't I do that? I made a mistake. So why can't I do that? What's wrong with that? It's because the reason why this is wrong, and I didn't notice it till I went to draw all the bonds, is that would give nitrogen 5 bonds. Okay, that's not allowed. So let's go back. So that's not one of our options at this moment, because we can't give the nitrogen 4 bonds, or 5 bonds. It just can't take 10 electrons. So let's try another one then. So we have a lone pair, which is, or we have a pi bond that is here attached to this nitrogen that has a positive formal charge. So we have a pi bond that is next to an atom with a positive formal charge. So we're using the third, I think, the third tip that they gave you, the third pattern to recognize. So what I'm going to do instead here is I'm going to erase this arrow, and I'm going to put a different arrow. This arrow is going to be the pi bond attached to an atom with a positive formal charge. And so we can do that. And let's see how that works for the nitrogen. And so we'll have the nitrogen here. It now has a lone pair. It now has 3 bonds. But this oxygen now has 1 bond and 2 lone pairs. So it's lacking. It also doesn't have an octet. So this isn't so good of a structure either, right? We want each of these to have an octet. So oops, okay. Well, that's not so great either, is it? So let's try something else then. We do have a lone pair allylic to a double bond. A lone pair allylic to a double bond. And it's this one right here, the one on the oxygen on the far left. It is on the nitrogen. It is one away from the nitrogen, which is on the double bond. So let's try this one more time and see if we get something that works. All right, so now this oxygen. Now what's the problem with that? Well, remember, allylic lone pair requires 2 arrows, because we would be exceeding an octet here if we did that with nitrogen. So that's what we'll do. We'll go like that. Okay. And that works. So we've got still this double bond. We got a nitrogen now. It's got a, whoops, I lost my other arrow. Okay. And this nitrogen is now double bonded to this oxygen. And now there's a single bond to this one, and now it has 3 lone pairs instead of 2. So it has this -1 formal charge. The nitrogen is now, let's see, it's in the same situation it was before. 5 bonds, no lone pair, or 4 bonds, no lone pairs. So it has a +1 formal charge. Remember, it would have no formal charge if it was 3 bonds, 1 lone pair. but it's got one less dot than that. It's got, if we split the bonds in half, it's got 1, 2, 3, 4 dots instead of its usual 5. Okay, so that works. And then we have one more situation that could happen here, and this is a kind of combination of things that we'd have to do. If we look right here, and it's because we can't exceed the octet on the nitrogen, but what we can do is, if we do this right here, we can or essentially, no, let me start from here, it'll be easier. Sorry about that. So what we can do, I guess it's the same, but we can make this a double bond, but this nitrogen now will be exceeding an octet. So what we can do is we can go like that. Or the other possibility is actually, just to make this stated better in terms of your 3 rules. So here we have a pi bond attached to an electronegative atom. A pi bond attached to an electronegative atom. And so that would be, if we're going back a little bit, it's this one, number 4, pi bond between 2 atoms of differing electronegativity. So here we would end up with a oxygen here with 3 lone pairs. So both of them now have 3 lone pairs. And we'd have a nitrogen with 3 bonds and no lone pairs. So now that is a positive 2 formal charge, because the nitrogen should have 5 dots, but it's only got 3. And so this is where this last move can come in now. The move I tried to do at the beginning. I couldn't do it because it made the nitrogen exceed the octet, but now it's only got 3 bonds. It's deficient of electrons. And so we can now do this move right here, and that will be now legal because we won't exceed the octet. And so now you have a double bond to the nitrogen. We still have these guys here. And so now we have, again, a nitrogen with 4 bonds and no lone pairs. So it has a positive 1 formal charge now. But this carbon right here, again, it had 2 hydrogens to start. So now it has 3 bonds, 1 here and 2 others, and no lone pairs. So it has a positive 1 formal charge as well. So in terms of the the resonance contributors, these 2 on the far right have way too much formal charge. So they're not going to be significant contributors. This one here will be a significant contributor. These 2 both. It has the lowest amount of formal charge possible given the structure. So when we're determining the stability, the octet rule is usually the most important factor. Being deficient of an octet is highly unstable. So here, for example, the carbon is deficient of an octet. So this is not a particularly stable situation. So what we can do instead is we have a lone pair that is adjacent to a positive formal charge. We can make a double bond there, and that leaves this oxygen with 1 lone pair, so it's got 3 bonds and 1 lone pair. So that gives it a positive formal charge. So this second structure is more stable than the first one, because in the first one the carbon did not have an octet. It had 3 bonds and no lone pairs, so 6 electrons around it. Oh jeez, oh no, what did I do? Okay, there we go. it has 3 bonds and no lone pairs. So that's 6 electrons around it. That is not an octet. But once it has the double bond, now it has an octet, 4 bonds and no formal charge. This oxygen has a positive formal charge, but it also has an octet. 2 electrons here, 2 in this bond, 2 in this bond, that's 6, plus 2 more, that's 8. So this second one would be the more stable one. So this is the more stable one. More stable. More stable. For the next one here, what we have is a lone a positive formal charge adjacent to this double bond here, and so what we can do is we can like that. So we have pi electron next to a positive formal charge. That's what this one is. Pi electron next to a positive formal charge. And so now this carbon was making 4 bonds. Now it's only making 3 and has no lone pairs. So it's going to have a positive formal charge. This nitrogen will now have a lone pair right here, and it will be making 3 bonds. So we'll have 0 formal charge. In this case, the more stable structure is the first one. And the reason why is because, again, this carbocation, it is lacking an octet. That's not very stable. And so this nitrogen did have an octet. It had 2, 4, 6, 8. 8 electrons around it. That's an octet. Even though it had a formal charge, which isn't ideal, at least it had an octet. So the ones with the octets are the more stable resonance hybrid. That's the bigger factor. Formal charge comes after that. Having lesser formal charge is important too. Finally, let's talk about what resonance means for molecules. And in particular, what we've talked about is that same nectarine example of being, partially one fruit, partially another, but really it's its own fruit. It's that mixture, maybe not 50-50, but it's a mixture of all these things. And when it comes to resonance, the true structure is a hybrid of all of the structures that we might write, and weighted by, which is more stable. So this is due to the fact that electrons are not localized. They're delocalized when they participate in resonance, meaning they are free to move between the p orbitals of sp2 hybridized atoms, and so they are delocalized. They aren't attached very strongly to any particular atom. They can move around in wherever is indicated in the resonance structure. So to be delocalized, electrons must exist in an unhybridized p orbital, so not a hybridized orbital, so that it can have that sideways overlap with other p orbitals. And to be delocalized, the electrons themselves must be on an sp or sp2 hybridized atom, if the electrons are on the atom. So here we have another example similar to ones we looked at before of resonance structures. So does a delocalization of the electrons in the imide create a more or less stable contributor? So the one on the right is less stable because of the formal charge. So this resonance structure, or the true resonance hybrid, is going to look more like the structure on the left, but there will be a little bit of the structure on the right. And the result of this is that what it does is it spreads out the charge so that it's not as much in a single particular place. And what that means is that the molecule will be more stable. And what we mean by stable is less likely to undergo a chemical reaction that will convert it into something else. And this is, when I think of a chemical reaction, an analogy I make is, the sticking of magnets. When magnets stick, that's like positive sticking to negative. And when molecules collide and react, it's often because a positive portion of the molecule is attracting to a negative portion of the molecule. Well, if you spread out that charge over a greater area, the attraction becomes less. You can think of it like a really strong, tiny magnet that will stick really hard to your fridge, as compared to one of those like magnets you get from the plumber or the pizza delivery place, where the magnetic attraction is spread over a wide area. It's not as likely to like hold up a piece of paper or something as the one that has the strong attraction in the small space. And the same is true here. The small, when the attraction is spread out over a big range, or that charge is spread out over a big range, that means less likely attractive force resulting in some chemical reaction. And so we say that the delocalization of the electron stabilizes the molecule and can make it less reactive. So in terms of delocalization, some atoms that would normally be sp3 will become sp2 hybridized. This depends on the atom. You'll want to look at how many bonds it is, calculate the steric number, and that's how you will know what the hybridization is. For example, here the nitrogen starts as sp3 hybridized, but when the resonance when resonance occurs, it goes into sp2 hybridized. Because, for example, here with this amide, as it's called, there's a kind of functional group called an amide. The result is that the nitrogen would end up having 3 bonded atoms and no lone pairs, and so that results in sp2 hybridization. And the question is regarding like oxygen, nitrogen, carbon, why is sp2 hybridized less stable than sp3 hybridized? Well, it's because in the non-formal charged arrangements, a lot of the times there's going to be sp3 hybridization, like the most common situations where oxygen is not every situation, but when oxygen is like this, or when nitrogen is like this, the most common and most stable bonding arrangements are those in which the oxygen is making 2 bonds and has 2 lone pairs, nitrogen is making 3 bonds and has 1 lone pair, the carbon is making 4 bonds, and those are all sp3 hybridization situations. The sp2 hybridization of the nitrogen causes the nitrogen to be trigonal planar in this molecule. So the result is that this has an impact on the shape of the molecule. The nitrogen is going to have some sp2 hybridization character to it the entire time, so that the electrons can travel through into the p orbital, the unhybridized p orbital. So remember, if it's sp3 hybridized, there's no p orbitals left. It has to be sp2 hybridized to leave 1 unhybridized orbital for those electrons to go in. And so for those to overlap, these all have to be in a plane. And so it's a sp2 hybridization all the way along this region from oxygen to carbon to nitrogen due to that resonance. So sometimes, as we saw a few examples where if you have a lone pair adjacent to a double bond, there can be resonance, but that will not always be true. And the reason why is because if we look at this one right here, this nitrogen, for example, if we have a lone pair that's allylic to a double bond, so we use 2 arrows, and it results in this shape. But that shape is not a valid resonance structure, and the reason why is because of the ring. The p orbitals can't overlap and line up in order to form the proper pi bond. And so it has to do with this. So the delocalized electrons must exist in unhybridized p orbitals that are overlapping, sideways overlapping with neighboring p orbitals. The problem is that the nitrogen's lone pair is not in that plane. It's over sticking off to the side in this flat molecule. And so the result is that these electrons are not accessible to these unhybridized p orbitals. And so that's something that it's an unusual situation. It's hard to spot, but this is one of those situations. This nitrogen just can't form two pi bonds like this. And so basically, like a pi bond, one on either side, is not going to be possible unless the molecule can straighten out. That's the easy way to see it. So an example where you got two pi bonds on the same atom is carbon dioxide. But that is because those pi bonds can be perpendicular to one another. Because this molecule can be in a line, this cannot result from that. And so the lone pair is here off to the side, and it just is not accessible to these p orbitals. And that's the end for this week's Chapter 2 lectures. Thank you for joining me. Please let me know by email or in lab or somewhere that if and when you have questions. And I will see you soon. Have a good week.